Inertial confinement fusion. Introduction. Inertial confinement fusion is a method of fusion energy production that involves the rapid, high-pressure compression of a fuel mass. This compression produces high temperatures and pressures that cause the atoms at the center of the fuel mass to fuse together, releasing large amounts of energy. This energy can then be used to power a variety of applications, including electricity generation, spacecraft propulsion, or even for military or research purposes. ICF is considered to be particularly promising because it has the ability to produce large amounts of energy from relatively small fuel masses, making it a potentially cleaner and more reliable alternative to traditional fossil fuel-based methods of energy production. In this essay, I will discuss the physics of ICF, some of the limitations and challenges associated with it, as well as the potential applications of this form of fusion energy. The basics of inertial confinement fusion. At its core, ICF is based on the process of nuclear fusion, which is the joining of two atomic nuclei to form a single, heavier nucleus. This process releases large amounts of energy, which has the potential to be used in a variety of applications. In order to produce such a reaction, the two nuclei must first be brought very close together, and then held together long enough for the reaction to take place. This is known as the confinement part of the equation, and it is the key to making ICF work. The basic idea behind ICF is to compress the nuclei together quickly, in order to create a sustained reaction. This is usually done by firing several laser beams onto a fuel pellet, which is typically composed of either a traditional fusion fuel such as deuterium or tritium, or a relatively new type known as a hydrogen-boron fuel. These laser beams are typically fired simultaneously so that they converge at a single point at the center of the fuel pellet, which creates an enormous amount of pressure on the fuel mass. This pressure compresses the nuclei, driving them together and triggering a nuclear fusion reaction. For a successful reaction, the pressure and temperature generated must reach a point known as ignition. When this occurs, the fusion reactions that are created are self-sustaining, and will continue until the fuel mass is completely consumed. The amount of energy produced in the reaction is largely dependent upon how much of the fuel mass is consumed and how many reactions take place. Limitations and challenges of ICF. The primary limitation of ICF is the associated cost of setting it up. For a given fuel mass, this cost can be extremely high, making it difficult for countries or research organizations to experiment with or implement it as an energy source on any large scale. Additionally, there are still some technical and engineering challenges associated with making ICF work. Because the reactions take place in a very confined area, it is difficult to ensure that the heat produced by the reactions is conducted away from the fuel mass quickly enough to avoid overheating. This can lead to what is known as a thermal runaway, which is an uncontrolled situation where the temperature increases rapidly and causes a premature end to the chain reaction. In addition, there are potential safety risks associated with ICF. In particular, if the fuel masses being used in an ICF reaction contain certain radioactive elements, then they could potentially become unstable during the course of the reaction, leading to a potential nuclear accident. This risk has led to concerns that ICF could potentially be used to develop nuclear weapons. Potential applications of ICF. Despite these challenges, there are a number of potential applications for ICF. For instance, it has the potential to be used as a clean and efficient energy source, replacing traditional fossil fuels and providing a renewable source of energy for the future. It could also potentially be used in spacecraft propulsion, allowing for high-speed, long-distance space travel. Finally, it could also have military applications, such as providing a powerful weapon against potential adversaries. Conclusion. In conclusion, ICF has the potential to be an important form of fusion energy production. Although there are still some challenges associated with it, ICF has the potential to make a significant contribution towards reducing our dependence on traditional fossil fuels. Additionally, its potential applications are vast and varied, potentially providing a powerful tool for energy generation, spacecraft propulsion, and even military applications. Overall, ICF is a promising form of fusion energy production that has the ability to revolutionize the way we use and produce energy in the future. Don't forget to like this video and subscribe for more great videos from our channel.